Okay, which of the following is the graph of y equals 0.25 cosecant x plus pi plus 1? I think this extra parenthesis right here is a typo, so ignore that. So obviously we have a few transformations here. We have an a value, which is a vertical compression, but we're not going to wind up using the a value to identify the graph. So you can pretty much ignore the 0.25 in the front. We have a horizontal shift, and the horizontal shift which occurs on the inside of any function is always the opposite of the way it looks. So if you see a minus sign, it's actually a shift to the right, and if you see a plus sign, it's actually a shift to the left. So this graph will be shifted to the left pi units. And then we have this plus 1 on the end. That's going to be a vertical shift, and this one works the way we would normally think. So plus 1 will be a shift up 1. So we are going to use really the fact that it's left pi and up 1. We're going to use those two pieces of information to narrow it down. And we're also going to use the period. There is no b value showing. If there was a b value, it would be right here. But see how there's no number there? The b value changes the period. So since there is no b value, that tells us that the period has to be the usual 2 pi. For secant, cosecant, sine, cosine, they'll have a period of 2 pi. So really, these are the three pieces of information that we're going to use to narrow down our search to the right graph. So let's start with up 1. So this tells us that the midline right through the middle of the graph should be at 1. This graph, the midline is 0. So that tells us that this is not the answer. So we've eliminated 1 so far. This graph seems to have a midline of 1, so that's okay. This graph seems to have a midline of -1. Alright, so we can eliminate that graph. And this graph does have a midline of 1. So just from that, we've narrowed it down to a 50-50 chance between this graph, the second graph, and the fourth graph. All right, so now let's see if we can use the period. So we used the up 1 transformation. Now let's see if we can eliminate one of the choices because of the period. So the period has to be 2 pi. So that means from corresponding point to corresponding point, okay, that has to be a distance of 2 pi. And looking at how the graph is marked, from here to here is 2 pi. So that looks about right. So can't eliminate that. So that seems like the same thing going on here. From here to here, that's the period. And again, looking at this graph, from here to here is 2 pi. And that looks about the same. So sometimes that helps us eliminate options, but this time the period didn't help us narrow anything down. Okay, so that means we have to turn our attention to the remaining piece of information, which is left pi. Okay, this is the most complicated one, because to use this, we have to do a whole graph of our own, and then imagine shifting it around. So that's what I'm going to do. Remember that cosecant is the reciprocal of the sine function. All right, hopefully you have that memorized. So that's why you're about to see me graph the sine function. All right, because that's how you graph cosecant. You start with the sine function. Okay, so period of 2 pi. So this will be 2 pi, and over here I will have negative 2 pi. So that makes this pi, and this will be negative pi. And I will put additional guide marks in between. So the sine function looks like this. The sine function unshifted starts at 0, and it goes up, and it comes down, and it falls, and it comes back. Okay, so this is what the sine function is going to look like. All right, I'm going to just repeat that for one additional period. Okay, one of my neighbors is having some allergies or something. I wonder if the video picked up that tremendous sneeze. Okay, so this is the sine function. We know that there are asymptotes, which I will do in gray. Anywhere the sine function touches the x-axis, there should be an asymptote, all right? Because you can't divide by 0. And if the sine function touches the x-axis, that's 0. So there should be an asymptote here, and an asymptote here, and an asymptote here, and an asymptote here, and an asymptote here. Okay, so the cosecant function touches the top of each hill and the bottom of each valley. So there should be a loop of the cosecant function right here, reaching towards these asymptotes, and there should be another one down here, reaching down. All right, similarly, there'll be a loop of the cosecant function here, and there will be another loop facing down right here. Okay, but now we have to shift left pi. So let's see. So remember that pi is it's 2 marks on this graph, or pi is the distance between asymptotes. So if I shift left pi, then for example, this loop right here is going to shift over here. Okay, all right, I just shifted this to the left. And this loop right here, if I shift it to the left, it's going to end up over here. Okay, so focus your eyes on these red loops. Ignore all the gray ones. The red ones are what the actual cosecant function would look like. Of course, it will be shifted up 1 as well, but we should have an upward facing loop to the left of the y-axis, and we should have a downward facing loop to the right. So let's see if we can use that to narrow down to the final answer. So on this graph, is this going to be the correct graph? No. We're expecting to see an upward facing loop to the left of the y-axis and a downward facing loop to the right. This one has a downward facing loop on the left and an upward facing loop on the right. So that tells me that this graph is not the answer. That means the last graph must be the answer. And sure enough, I look at it and I see an upward facing loop on the left and a downward facing loop on the right, just as we predicted. All right, so let's just check our answer, and there you go.